Kevin Barry is actually going to be talking to us about remarkable economic returns from permanent space infrastructure. Kevin Barry is actually a student of history, an avid gamer, and a business analyst. He has published several papers in historical economic trends and how they apply to commercial space development, observing the correlation between the rise and fall of civilizations and the quality of their infrastructure. Kevin Barry is an active member of ISEC and part of EFRAF's financial subcommittee, as well as infrastructure consulting specialization in space, business development, financial analysis, and thought leadership. Thank you so much, Kevin Barry, for being a part of Blue Marble Week. Take from here.
Okay, so I just want to start out by saying thank you all for being here, and I want to address Chris's points from earlier. Unfortunately, it seems that he has left the call today. But when considering the economic value of a space elevator and the true value that we can derive from it, the purpose of my presentation today is to really change where that paradigm is heading. In order to do this, I'm going to go over 4 different major points to analyze what is the value of a space elevator, how do we fund one, and how is the space elevator conversation need to be changed in order to fully understand and validate the reason for building one. It is, at the end of the day, no matter how you cut it, a very expensive endeavor that, because it's never been done before, is just inherently risky. And being able to address those concerns, I think, is the chief reason for having panels like this today with Blue Marble Week. So I know that many of you here, I'm just preaching to the choir. One of the first things to address is just simply, what is the value of space? Why do we even care? I mean, we've had plenty of panelists already today talking about the value of having, hundreds of thousands of ton in orbit, but to what end? And I would argue that there are really 5 major categories of reasons to go to space. Extraction alone is one of the first things people can think of and understand, whether it's mining minerals on the moon, Mars, or even the thousands of asteroids that actually orbit even closer to Earth than the moon, let alone the asteroid belt itself. The mineral values in these generally have mineral concentrations in excess of 150 times the richest veins that we can find on Earth in terms of density. And you can find figures that give, frankly, ludicrous values, where asteroids in the asteroid belt have an estimated mineral value in the quintillions of dollars, more than a 7-fold increase the entire Earth GDP. Space solar, as has been discussed here, is an immense resource, to say nothing of just even orbit around Earth. There is a huge amount of solar capacity that we can embrace, building up to sort of the very, very long-term ambitious goals of something amounting to a Dyson swarm. And even just water in space, based on our launch costs and based on the difficulty of getting things there, just having liquid water in space is worth thousands of dollars per kilogram. And as rockets have gotten better and better, this number is dropping, but it's still an extremely valuable commodity, even though it is basically free on Earth, just simply because of its outside of the gravity well. Scientific, this is one of the primary uses of space, is to go in, analyze on the International Space Station different experiments in microgravity, better understanding the radiation environment, astronomical observation outside of our atmosphere, where we get a more unobstructed view of the universe around us. There's certainly far more than I need to discuss here about the scientific value that we can derive from being in space. Observation and communication from satellites, GPS, the Copernicus constellations, Starlink's ambitions to provide global internet. There are many uses of having near-Earth observation satellites and communications relayed through orbit. and it has allowed a massive proliferation in the ability for humanity to communicate all over Earth and increasingly in space as well. Looking a little further into the future, constructs will also eventually start to make a major impact on what is the value of space. That, quite simply, expansion into space affords a massive opportunity even beyond colonization. The mention of constructs like the giant O'Neill cylinders, which provide centripetal acceleration in large rotating cylinders, space hotels, refueling depots, stations. There are a myriad of different objects of various mega engineering scales that could eventually be constructed in space, as there is almost an unlimited amount of real estate to expand into and to construct. And finally, we've touched on this in the previous presentations, there is an immense existential value to being in space. Life is exceedingly rare on Earth, if not unique to our planet. And being able to not have all our eggs in one basket on Earth is of great value. And besides, taking and focusing humanity on looking up and to the stars is a much better use of our resources and our time than trying to look around and point fingers at each other and use our, capabilities as a species to, try and fight over limited resources on Earth when there are so many things that we can extract and utilize and use in space. So these 5 categories are sort of the building blocks of why we would even care about going to space in the first place. And, as we've begun to mention here, there are lots of ambitious opportunities. The space solar power, as has already been discussed, the increasing number of mega constellations, developing a cislunar economy, and the Artemis program's goal to create the Gateway space station and eventually develop a connection to the lunar surface, whether it's for Minium, Helium-3, going after lunar ice, or any other number of uses that we can have. The moon as our closest celestial body is a very reasonable target. Moving on beyond that, this is the graphic, which I'm sure you've all seen, of Musk's ambition to colonize and utilize the surface of Mars. And all of these have huge mass requirements. To figure out how to get to these places is very difficult. And this is much of the limiting factor that my colleagues have already addressed. Getting these objects into space is, with the rocket equation, very draconian. I won't reiterate what she said, but in short, even with 3 launches per day, which is 10 times our current rate, that would take 183 years just to get this 1 million tons to Mars. And with space solar power, any number of the other things that we've already discussed here, that number just continues to bloat and grow. And while it is certainly plausible that Starship will be able to launch multiple vehicles, there very quickly becomes limitations of the environment, of being able to achieve more launch windows. And ultimately, even if Starship is everything that we hope and dream it can be, it still has a limitation of sending rockets only every 26 months to Mars, because we have to wait for planetary convergence and to travel along the most efficient paths. And there's a 9-month journey in between when we leave Earth and when we arrive at Mars, and having to wait on the other end. And these factors just make it so that it is very difficult, and there are very high barriers to entry to accessing space for any of the reasons discussed. But I would argue that actually kind of our most limiting factor is shown. This is an old picture of what Singapore looked like. And that there isn't sufficient infrastructure for space commercialization. And in many ways, space is an outpost. It's something where we can send objects, they're there for a couple of years, but then, or maybe 15, 20 years, but ultimately, they have to just be put in disposal orbits or left where they are, like a car running out of fuel on the highway. And it's not really a commercial environment so much as it's a speculative venture, and that without building up that infrastructure, that's really all that's ever going to become. Building up the highways, the trains, all of these metaphors of infrastructure we have on the ground is what is going to be necessary to achieve true commercialization in space. And so for my purposes, I've looked back at history and how we value infrastructure. And I think one of the simplest analogies of why infrastructure is so valuable is this simple analogy here. If you have something like a rowboat and you're trying to cross a river, rowboats are an easy technology. Like rockets, they exist, we have them, you can use them to cross the river. But if you are a farmer and you have a few thousand tons of grain, even though you have a rowboat, and you could probably build a whole bunch more rowboats, it becomes wildly impractical to manage shipping 1,000 tons of grain across even a small river, just in a rowboat. Your chance of spillage, your chance of just congestion in the river, just becomes overwhelming very quickly. And by comparison, a bridge is much more expensive and difficult to construct that first time. But it allows wagons to cross that bridge, and it allows something like the concept of shipping 1,000 tons of grain across a bridge to be almost trivial. That there doesn't even need to be a toll. That bridges allow and facilitate access in a way that just simply wasn't possible before, even though transport may have been. And that is, I think, that the core of what infrastructure does, is that it allows decreased transaction costs and increased access, giving you new market opportunities, and that it is observed empirically that a linear decrease in transaction costs has a exponential effect on the market growth and gain, just from the network effects and the growth of opportunities that become viable once you have these decreased transaction costs. And so when you take and have a conversation centered around how much can I charge for somebody to cross the bridge, it's really kind of a self-defeating argument, that infrastructure at its very core is about decreasing transaction costs. So by charging a transaction cost, you are in fact countering the original purpose of having it in the first place. So as a historical example, I looked a lot into the Transcontinental Railroad. And the Transcontinental Railroad, shown here sort of in the orange and green line, was a very significant project for the United States to embark upon. And it allowed transport between New York and California to go from a 6-month harrowing journey to a 1-week casual trip. That in the end, it allowed the country to be joined in a way that it never had been before, not just because of the train line, but because of the telecom line, which you can see here on the right-hand side. That connecting these two sides of the country had a big impact, and it made new businesses entirely possible. Oranges grown in California were suddenly be able to be sold in New York, something that would be unthinkable without it. And to pay for this very expensive, difficult thing, which many other people have discussed, there were two companies, the Union Pacific and Central Pacific, which competed and were paid per line mile that they constructed. And this competition meant that they were trying to see which of them could build further, and they were paid in large part by grants from the U.S. government of large swaths of land. In fact, 20 square miles of land per line mile of rail built, and that the value of the railroad was not in the railroad itself. In fact, within 10 years, despite all of the success I've just mentioned, the Transcontinental Railroad companies all went more or less bankrupt. The only ones that kind of survived was Southern Pacific, and Union Pacific was, heavily subsidized and basically prevented from failing. But all of these railroads were actually not very good businesses. But the financiers of the project, the US government, and even the individuals behind this became exceedingly wealthy because of the massive increase in value that the Transcontinental Railroad provided, and that the land, all of the mines, all of the cities along the railroad were really where the true value lay. They didn't make money from having people pay fares to ride on the trains. That was necessary to maintain the train, but the rail itself was not about the transaction costs on the railroad. It was about the opportunity to say, I want to go mine something in the Rocky Mountains and bring it to Chicago. And that suddenly all of the value of the Rocky Mountains was at the access of the whole country. And that the immense value you get from just the ability to move something from one place to another was what created so much of this value. And in many ways, to finance this project, the land itself was used as the speculative value and basis to pay for this, and that it wasn't based on the value of the trains. It was based on the value of the land and being able to reach that land, and the value that the land would be after the railroad was constructed. When before it was constructed, the land was basically free. Anybody could go out and settle it at no cost, and yet the land around the railroad was so much more valuable. Now, looking at another case, Panama Canal, which is a full presentation and story into itself, but much like what we are trying to talk about here with the space elevator, the Panama Canal actually had a long history dating all the way back to Thomas Jefferson and Napoleon. Thomas Jefferson, when he originally commissioned Lewis and Clark, he also sent out explorers to explore whether there was a passage or how you would get across through Latin America, and actually purchased this area that you can kind of see here in yellow and red, that the easement that was acquired by Jefferson was what actually enabled the construction of the Panamanian Railroad, and that the American Railroad, which was constructed several years before the Panama Canal existed, was actually the fastest way to cross between the oceans, and was a huge part in the actual success and construction of this gargantuan mega project, which created Gatun Lake and many of the other structures shown here. But that the development of the infrastructure of building an entire city for the workers, of bringing in the different drilling rigs and being able to bring them along a railroad were all required to do this. And the US government used its naval power in both oceans in order to protect and even change the governance in Panama to facilitate the creation of this project. And that, if it weren't overshadowed by the beginning of World War I, only a few months after the completion, the Panama Canal has had massive geopolitical impact in allowing the United States to connect its coastlines in ways it would not have been able to do before. And this is another key point about infrastructure, is that infrastructure in many ways has an understated impact in our economy because, again, as a business, it just doesn't really perform very well. This project took more than 100 years and bankrupted France to construct. But it has since paid huge dividends in the value it has delivered for countries around the world in being able to traverse this canal only about 15 miles long. And so, when we look at the space elevator here, and this is ISEC's rendering of what they think one of the three main nodes is going to look like. It doesn't really make sense to talk about it on a cost per kilogram per year, because space elevators are not about charging a transaction cost, nor does it really make sense to look at it from what does it cost to build this thing? Can we charge like overhead fee? Like, how do you value space elevator? Nor does it make sense to be like, well, whatever Bezos or whoever else will pay us, that's how valuable it is. we could have a further conversation about, what is the cost of not having a space elevator? How much is it going to cost us to solve it in other ways? And I would say that at the end of the day, they're just not a good business. There's no way to cut it that space elevators are in and of themselves a good business, but they are great economics. They facilitate a huge proliferation of economic activity, seeing what could happen in the geo region, in the apex region. The ability to connect to anywhere in the solar system is of immense value, and that the value of a space elevator is not about what is the space elevator worth. It's about what is space worth, and what does the space elevator allow us to access and allow the economy of Earth to reach out beyond our orbit and reach these other things, and that the space elevator is in many ways a very effective tool to do this. So digging a little bit in the nitty gritty, the history of the space elevator is also quite interesting. In short, I think that the biggest premise for me in the understanding of a space elevator is to embrace that the space traction elevator is a relatively new concept. People have thought, Tower of Babylon style, or this Eiffel Tower that is actually a tower to space for a long, long time. But the traction cable, in the idea that the space elevator is hung in the sky based on the centripetal force that is felt by just swinging around Earth, is a new concept that was developed by Yuri and was, made much more publicly available by Jerome. And that, largely the recent history that we've seen with space elevators has been around this identification that the material of the traction cable itself is really the bottleneck. And there has been hype, based on the development of carbon nanotubes, and that this sort of following the hype of, well, what is this prerequisite material? How do we get it to start? And all of that hype that we first saw when we had carbon nanotubes, it kind of fizzled because there wasn't a clear way of delivering on the material promises of that. And now we have, sort of this iteration, which I'll leave Adrian to discuss further, of the development of more 2D materials, which have similar tensile strengths, but more ability to be created and, in future to be manufactured at the scale necessary to achieve these projects. And that, the benefits of a space elevator allow this space infrastructure that we've discussed about how there's a massive movement of cargo along the space elevator, but it's more than just the ability to move something in orbit. Honestly, rockets are pretty good at that, especially into LEO. Space elevators are much more about the ability to move things far beyond GEO. That, David and Goliath style, when you take and you have 100,000 kilometer long sling around Earth, the kinetic energies that you can throw an object off of the end of that just dwarf anything that a chemical or even nuclear powered rocket can achieve in the short term. And leaning into that more and using the acceleration you get from falling away from GEO along the space elevator allows you to achieve immense speeds to deliver mass in reasonably high quantity anywhere in the solar system, if not interstellar. And that is just something that is just not achievable by rockets. Even if there is a level of price parity, of price cost, the uninterrupted exchange, the reliability, and the ubiquitous access to space elevators provide makes it so that, much like the original bridge I was talking about, a bridge is stable. You can depend on it. You know what throughput it has. You can plan for it. You can do the thing. It won't congest the river with traffic. It won't have spillage. It doesn't create as many problems as you get when you try and do it piecemeal. And that the business opportunities that this allows in the different economic regimes is really the main focus of where we should be looking. And so, looking at how to fund this, drawing upon those historical cases, it seems that there's much of a balance here of financing of any project. You have to take and say finance does not create value, but it does allow you to borrow against the future and say, this thing that I am going to give you access to has more value, but I need to pay this barrier to entry cost to get there. And if you can substantiate the value, much like what was done with the Transcontinental Railroad, of how valuable that land will be as your collateral, and you get a loan from a financier, whether it is a bank, a government-backed debt, however you get it, that finance allows you to reach beyond what money you have available, that rather than funding this based off of equity infusions and grants given to the space elevator, those are not necessary ultimately if you can prove there is a greater value in having a space elevator than there is in not having one, and that I can pay interest on the difference. Then you are able to build towards and finance the creation of a space elevator based on the infrastructural investment. And infrastructure, again, from a huge preponderance of evidence, is a very low default rate. Even in developing countries in Africa, we see that infrastructure development has a failure rate of less than 3%. And it has returns for terrestrial infrastructure in excess of 20% compound annual growth. And that is just a very reliable institutional scale investment that can be made when you have the patience of large long-term institutional investment. Even if it doesn't necessarily make sense as a short-term business opportunity, because it might take 10, 15, 20 years to build it in the first place. And I'm just going to gloss over ISEC's approach here, as I'm sure it will be discussed in much greater detail by my colleagues here. But in general, ISEC's approach is to have various ground-based infrastructure from the HQ, ocean transport, and the marine node and the earth port connecting along the tether cable to the geo node, allowing for interplanetary payloads going up to Apex, and to facilitate this tenuous line here, this tether connection with the development of 2D printable materials, and that to build up the engineering validation and to move through this chart here through engineering verification, design validation, to demonstrate how the product can be done through the process of building out the pathfinder, seed tether, and eventually the initial operating capacity of the space elevator. And then moving on to reinforce and build up the structure to achieve the full scale vision. As Swan stated earlier in the presentations today, we are just moving out of this technological feasibility stage where we have shown in a lab that the materials that we can develop do have this technical capability. And going through engineering verification of seeing how this material behaves outside of the lab, bringing it up to scale, those are all projects that do need solutions. And I don't today have the answers of what those will be, but the process has begun. And as this process begins, the business development and the concept of how do you fund this, how do you go through that research, how do you build it up from the dream that we have today to the reality that we can build in the future. And that's the next part that I want to kind of go in and discuss. In general, I think that the discussion between public, private, and sort of a hybrid public-private partnership is a discussion that is perhaps beyond the scope of the presentation today. But I'll leave this slide up here briefly just to get a concept of how private entities generally have more agile product development, quicker start, and are faster off the block, but they just don't have all the advantages that you get from a public in terms of better geopolitical negotiation, more legal integration just out of necessity, and there is more challenges that you have in public where it's harder. it takes a lot more public agreement. You have to have longer agreement horizons dealing with the political cycle. There are a lot of challenges to public and to private, and that most large-scale projects of this magnitude really do need to embrace the advantages of both systems, much like the Panama Canal did during its creation, heavily supported by the U.S. Army Corps of Engineers, but also by a large amount of Texas oil and gas industry that provided a lot of the equipment necessary to actually create the canal in the first place. And so this business development approach, which I have worked on and developed with ISEC, shows that we're just at the very early days of this process, and that as ISEC has developed a increasingly robust technical plan for what we're hoping to achieve, the next steps here is to show what a 1,000-meter tether would look like, even on the ground, to start building a space elevator institute and develop that legal infrastructure, show how the space elevator works in space. And then after we've demonstrated it and gone through all of the engineering rigor to validate and prove this technology, start to develop the seed tether, develop the main Earth connections and all of the different nodes in the system, and build towards operating capacity. And through this whole process, going through and acquiring seed funding, moving on to Serial A based on the proof of concept shown here, allow a much more segmented approach where institutional funding, while the ultimate goal, is just an unrealistic ask to ask for the billions of dollars necessary to build the whole program. This incremental approach will have a much greater success pathway to achieving the space elevator in the long term. And so just to reiterate, right now, the needs for this is to build up the seed funding, to have core staff, business development, and to move this idea from a place of science fiction and a place of dreams, that we can have presentations and calls like the ones we're having today to say, how do we take these next steps? How do we finalize this technological feasibility and start to demonstrate the architectural design of Fitzer and Swan and all the other members of ISEC that have been working on diligently during the technical phase, and start to build up proven prototypes. And so with that, I'll kind of leave it here for Q&A that any of the audience may have.
Thank you so much, Kevin. The United States has always been a pioneer of infrastructure, and space infrastructure is no different. And the space elevator is just a part of that next leap. So while keep an eye on the clock, because we're going to be moving on to our next speaker at 11:45, we have a question from Chris Kent, who asked, as infrastructure, what would the life cycle of a fully functional first generation elevator system be? He went on to further iterate with the bridge analogy. Some bridges are long-lived, some not. Most are upgraded in place. The climbers parallel rail cars are presumably those would be swapped out for new models over time. But what about the tether itself?
So for the tether itself, I believe there are other people in this who can more cogently answer the question, but it is actually designed to be somewhat modular, like specifically to address the issue of just space debris alone. The tether is designed to have a multiple approach and to be replaced about every 7 years in different segments that it can be actively fixed and repaired. And as you correctly noted, or like Swan gave earlier with the repainting of the Golden Gate Bridge, it would have a level of ongoing maintenance cost, but that the comparative outlay of capital necessary to contribute that once the space elevator is in place is relatively trivial. That the goal of the space elevator is to achieve parity where whatever transaction cost it may charge would be for that ongoing maintenance, not for the initial capital construction of the project. And that is really a negotiation between what materials do you have, how much can they be repaired, and at what cadence does that need to be done.
That's really good. And Nara actually gave a good comment. She asked, we need to get the general public to understand the vital need to establish large-scale space-based infrastructure, which is very important. Do you want to add to that in any way?
Yeah, I mean, I would say that in general, I think one of the biggest pieces of infrastructure is the importance of declining costs and declining cost curves. That, when we take and look at something like the expansion even to America, the New World, with the increase in availability of sailing technology, development of compass navigation, of accurate timekeeping for sailing, you saw that as you have a linear decrease in cost, you have an exponential growth of economy on the other side. And this has been observed too in aviation in the last few decades here. We saw that, from post-World War II, where aviation was almost strictly a military focused endeavor that was something that was just in development. Right now in space, we're seeing kind of those parallels that, the Apollo missions were the, Wright brothers plane of our era, and that building towards, that first commercial plane is a really challenging task, and getting to that level where in a matter of post-World War II or World War II, only a few soldiers had been on planes. To by the 1990s, it was pretty much everybody in the middle class and had been on a plane at least once in their lives. And I mean, that level of transition, that exponential curve, the cost of flight between World War II and the 1990s only dropped a little bit. Like, it was not a big change, but that drop in price made it so it became a near ubiquitous asset. And so when you build infrastructure of any stripe and you can decrease those transaction costs, it has a transformative effect on the economies that it in. And we've seen this again and again throughout history, whether it's canals, railroads, the transcontinental railroad, the building of the interstate highway system. Another great example of the interstate highway system is a garbage business. It costs a lot of money. It's not in well repair, and you earn nothing for it. The price of gas tax has been falling objectively since the 1980s, and yet the value to the United States is incredible. That a space elevator, like any infrastructure, is not a good business. There's no way I can say that it is, but it is fantastic economics, and it has this effect of being able to give a pile-on of, we can achieve all of the immense value in space by having a space elevator. Or really, today the discussion is about space elevator, but there are other technologies that exist that a space elevator enables, whether it be, an orbital ring or any other massive projects that are just not practical without having a space elevator as that first piece. And as our, lunar space elevator talk in a couple of days we'll discuss here, fantastic idea too. Very difficult to build one until you have a space elevator off of Earth. There's kind of a prerequisite step for all of these ambitions that we have. And once you have one, the other things become relatively trivial.
Very much so. So thank you so much, Kevin Barry. I'm going to ask if you could please unshare the screen. And we're going to be moving on to the next speaker. And as always, you can get more information at isec.org and at Foundation for the Future's website at f4f.space.